Hi chemists, I hope you're doing well and you're staying cool indoors. We're actually about to start our last big topic in chemistry, but before we do that, let's look at a quick review problem. All right, go ahead and see if you can answer this do now question. Okay, so this is a titration question, meaning that we're reacting an acid with a base. So we've got 2 liters of a 0.1 molar solution of acetic acid, and that's reacting with a 1 molar sodium hydroxide solution. And we want to know the volume of that. So we can go ahead and use the titration equation, right, which tells us that the molarity of the acid times the volume of the acid is going to equal the molarity of the base times the volume of the base. We know the molarity of the acid, it's 0.1 molar, and the volume 2 liters. And we know the molarity of the base, but we don't know the volume of the base. So we can go ahead and plug the numbers that we do know into this equation, and then we still have a variable for the volume of the base because we don't know that. Right? Then we can go ahead and solve this equation to get this number. So if you do that, you're gonna have 0.1 times 2 divided by 1. That's gonna give you a volume of 0.2 liters. So it's gonna take 0.2 liters of this base to neutralize all of the acid that we have. Awesome. Let's go ahead and get started with our new topic. So some of you might know that the Statue of Liberty is made of copper, which is also what pennies are made of. And you might notice that these two objects look very different. Right? Of course, one is tiny and one is enormous. But also, even though they're both made of copper, they have a really different appearance, right? Penny is very shiny and has that sort of characteristic orangey metallic color, right? The Statue of Liberty is not shiny, and it is basically kind of green, like seafoam aqua greenish colored. So even though these two substances are made of the same element, they look very different and they have very different properties. So we might want to think about why that is. Why is the penny so different looking from the Statue of Liberty? Well, it turns out that even though they're both made of copper, the copper that's in a penny is different than the copper that's in the Statue of Liberty. In particular, the copper in the Statue of Liberty has become what's called oxidized, right? Which is a fancy way of basically saying it's rusted. And so the copper in the Statue of Liberty has formed a compound, and that compound has different properties than just the pure element of copper. This is the reaction, or one of the reactions, that has happened to the copper in the Statue of Liberty. Right? So the copper can react with oxygen from the air to form copper 1 oxide. Take a minute to describe what's happening in this chemical reaction in terms of electrons. All right, so this is a chemical reaction where we're forming an ionic bond between copper and oxygen. The copper is getting a +1 charge, and the oxygen's getting a -2 charge. Right? We know oxygen always gets a -2 charge because it needs to gain 2 electrons in order to get 8 valence electrons. It starts out with 6, it has to gain 2 to form 8 valence electrons. The copper is a transition metal, and so it can have a charge of +1 or +2, but based on this formula, right, if we have 2 coppers and 1 oxygen, in order for the overall compound to be neutral, we know that the coppers in this particular compound have to have a +1 charge to bounce out the -2 from the oxygen. So that means that what's happening is that copper is losing electrons. Each copper atom is losing 1 electron, and each oxygen atom is gaining 2 electrons in this reaction. Let's think about why that happens. Based on what you know from what we've talked about this year in chemistry class, why does copper lose electrons and oxygen gain electrons? Okay, well, there's a whole bunch of different ways to answer this question, right? One would be based on the octet rule. We know that oxygen has 6 valence electrons, it needs to gain 2 to form 8. We can also explain this based on the type of element that we have. Copper is a metal and oxygen's a non-metal. And we know that metals characteristically lose electrons and nonmetals characteristically gain electrons. Or the reason that nonmetals gain electrons and metals lose electrons is because metals tend to be not very electronegative and nonmetals tend to be very electronegative. So another way to explain this would be in terms of electronegativity. We could say oxygen is a lot more electronegative than copper is. And so oxygen pulls really strongly on the electrons in the, from copper. And oxygen pulls so strongly that it steals copper's electrons. And copper has such a weak pull on its electrons that it just gives up its electrons to oxygen. So we can explain this in terms of the periodic trend of electronegativity, the type of element that we have, or in terms of the octet rule. Let's go ahead and look at another reaction. Take a look at this reaction and tell me what's happening in terms of electrons. Cool, so in this reaction, sodium and chloride are reacting together to make table salt sodium chloride. We know that sodium is going to lose one electron, and each of the chlorine atoms is also going to gain one electron to form the chloride ion. Let's go ahead and compare these two reactions. How are these two reactions similar to each other? You might have noticed that in both of these reactions, one element, the metal, is losing electrons, and another element, the nonmetal, is gaining electrons. We could also say, these reactions are both synthesis reactions, where two elements are coming together to form a compound. Awesome. This top reaction we know is colloquially sometimes called oxidation. When that word was originally invented, it was used by chemists to talk about something reacting with oxygen, right? Oxygenation. But nowadays, we've actually broadened the definition of oxidation, just like we did with our definition of acids and bases, right? We had a very narrow definition, and then we broadened it over time. And so both of these reactions involve oxidation. We've broadened our definitions. The oxidation doesn't necessarily mean that something's reacting with oxygen. It just means something's in a chemical reaction where it loses electrons. So both the copper and the sodium are essentially doing the same thing in these two reactions, and we refer to it with the same word. So oxidation is losing electrons. We also have a word for gaining electrons, which is called reduction. So in this chemical reaction, the copper is being oxidized, it's losing its electrons, and the oxygen is being reduced, it's gaining electrons. You can remember that with this acronym OIL-RIG, which stands for oxidation is losing, reduction is gaining, right? So OIL-RIG. Good, so in this reaction, copper is being oxidized and oxygen is being reduced. And so overall, this reaction would be called a reduction oxidation reaction because both of those things are happening. Something's getting reduced and something's getting oxidized. And reduction oxidation is a long, kind of unwieldy phrase. And so we usually shorten that to redox. And we'll say, okay, cool, this is a redox reaction. The reaction of sodium with chlorine is also a redox reaction. So let's take a minute to think about what's being oxidized and what's being reduced in this reaction. Well, we know the sodium is losing electrons to form a +1 charge, so it must be being oxidized. The chlorine is gaining electrons to get a -1 charge, and so it's being reduced in this reaction. Awesome. Let's go ahead and do some practice. I've pulled up 3 different reactions. For each of these 3 reactions, I want to know what type of reaction is it, what's happening to the electrons, they're going from what to what, what's getting oxidized, and what's getting reduced. Let's go ahead and talk about problem 1 together. So magnesium and sulfur are reacting together to make magnesium sulfide. If you look at your reference table, magnesium starts out with 2 valence electrons. It needs to lose those in order to follow the octet rule. And sulfur starts out with 6 valence electrons, so it needs to gain 2 in order to follow the octet rule. And so what's going on here is that magnesium is transferring electrons to sulfur. the two elements are coming together to form one compound. So this is a synthesis reaction in which electrons are flowing from magnesium to sulfur. So we said oil rig oxidation is loss, right? So the one that's losing electrons, that's magnesium, is being oxidized, and the one that's reduction is gain, so the one that's gaining the electrons, that's sulfur, is being reduced. Let's go ahead and look at reaction number 2. This is also a synthesis reaction because we again have two elements that are coming together to form a larger compound. In this reaction, let's see, copper is forming a +1 charge, oxygen is forming a -2 charge. So we've got electrons flowing from copper to oxygen. That means copper is being oxidized and oxygen is being reduced. If we look at the last reaction, this is actually not a synthesis reaction. This reaction is a single replacement reaction where the sodium is replacing the zinc in this compound. Even though this reaction is single replacement and not synthesis, it is also a redox reaction. We can figure out the flow of electrons and what's being oxidized and what's being reduced based on what's happening to the charges. So we're starting out with elemental sodium, which is neutral, and it's forming sodium chloride. So the sodium is getting a +1 charge. Meanwhile, zinc starts out in this compound, zinc chloride. So in this compound, zinc has a charge of +2, but it's forming pure elemental zinc with nothing else, right? Any element by itself is always neutral. So the zinc is going from +2 to neutral. The chlorine has a charge of -2 in this -1 in this compound, right? There's two of it, but there's each chlorine ion has a charge of -1 in this compound. And in this compound, chlorine also has a charge of -1. So we can talk about the flow of electrons. Sodium must be losing electrons and zinc is gaining electrons. So electrons are flowing from sodium to zinc. That means that sodium is getting oxidized and zinc is getting reduced. And chlorine is actually not getting oxidized or reduced. It's just hanging out in the background. That's what's actually called a spectator ion in a chemical reaction, meaning it's not actually involved in the reaction directly at all. It's just kind of hanging out. Awesome. So far, we've looked at reactions that involve ionic compounds, but we can also have redox reactions that involve covalent compounds as well, right? So let's take a look at this reaction. I want to know what type of chemical bonds are in the reactants and what type are in the products. So in the reactants, I've got a bond between hydrogen and a bond between oxygen and oxygen. Hydrogen and oxygen are both nonmetals. When they bond with themselves, they're going to form covalent bonds, and in particular, they're going to form nonpolar covalent bonds because the electrons are shared exactly evenly since they're shared between two identical atoms. In the products, water, we have a bond between hydrogen and oxygen, which are both nonmetals. So again, we have a covalent bond, but this is a polar covalent bond because the electronegativities are different. And so the hydrogen and the oxygen are not exerting the same pull on the electrons. So let's talk about how the sharing of electrons compares in the reactants and the products. The reactants have nonpolar bonds. That means the electrons are being shared evenly. The products have polar bonds, which means the electrons are being shared unevenly. Because oxygen is more electronegative than hydrogen, oxygen basically grabs the electrons closer to itself. So the electrons are still being shared, they haven't been transferred completely, but they're closer to oxygen and they're further away from hydrogen. That means that we can actually still consider this to be a redox reaction. In this reaction, oxygen hasn't completely pulled the electrons away from hydrogen, but it's partially pulled hydrogen's electron towards itself. And so in this reaction, hydrogen has partially lost an electron and oxygen has partially gained an electron. So we would consider hydrogen to be oxidized. Even though it hasn't completely lost an electron, it's partially lost an electron, and that counts. Oxygen we would consider to be reduced. Again, it hasn't completely gained an electron, but it's partially gained an electron, and that counts. So this reaction still counts as a redox reaction, even though nothing has completely gained or completely lost an electron. So reactions that involve forming covalent bonds can also be redox reactions. If we want to kind of summarize this up, if we're forming an ionic compound, then the element that's oxidized completely loses its electrons, and the element that's reduced completely gains electrons. If we're dealing with a covalent compound, a reaction in which we're forming a covalent compound, oxidation would mean there's a partial loss of electrons. The less electronegative element partially gives up its electrons and becomes oxidized. And the more electronegative element partially gains electrons, and so it becomes reduced. Good, let's apply this to this practice problem. So I have 3 reactions right here. I want to know which chemical is being oxidized and which one is being reduced in each of these reactions. Okay, so for the first reaction, magnesium forms a +2 ion and chlorine forms a -1 ion. So magnesium is losing electrons, that means it's being oxidized. Chlorine is gaining electrons, which means it's being reduced. In the second reaction, this is a reaction in which we have covalent bonds forming. So we're breaking some nonpolar covalent bonds between fluorine and fluorine and between nitrogen and nitrogen. We're bonding together nitrogen and fluorine. We know that fluorine is more electronegative than nitrogen. It's the most electronegative element there is. That means when fluorine bonds to nitrogen, it's going to pull the electrons closer to itself. And so it's going to partially gain those electrons. That means the fluorine is being reduced. The nitrogen is partially losing its electrons, so it's being oxidized. Good. The last reaction is sort of funky. It doesn't look like it, but this is actually a single replacement reaction. This is a reaction in which this copper ion would be part of a compound, something like CuCl2. It's forming solid copper, and meanwhile, zinc is now taking its place in this compound and forming something like ZnCl2. And what we've done is we've eliminated the spectator ions from this chemical reaction the way it's written. We just haven't bothered to write them in because they're not really important to the reaction. What's important is the elements that are gaining or losing electrons, the ones that are being oxidized or reduced. And so we've written this reaction only showing the elements that are being oxidized or reduced. But it's important to realize that in reality, inside the beaker where this reaction is happening, you're going to have some negative ions as well to balance out these positive ions. So the Cu2 plus is really part of a compound, and in the products, the Zn2 plus is really part of a compound. We never have positive charges by themselves without a negative charge to balance them out. Cool. In this reaction, the zinc starts out neutral and it forms a +2 ion. So the zinc must be losing 2 electrons. Copper starts out with a +2 charge and it forms a neutral ion. So it must be gaining 2 electrons. So in this reaction, zinc is losing electrons, that means it's being oxidized, and copper is gaining electrons, which means it's being reduced. Awesome. I hope that was helpful, and I'll see you all next time.